Okay, so okay. Sorry for calling you all guys on Sunday night, but I hope that you have signed in for interest. तो थोड़ा झेलना पड़ेगा. Okay. So today I'll start my lecture uh, with the concepts of sequence and series. I mean, we are going to finish sequence and series. Okay, I'm going to finish sequence, but I'm just going to start, and I think almost I'll just try to finish series by this lecture. So in the last class we have defined something. One definition is called limit n tends to infinity, limit lim-sup of xn is basically limit n tends to limit k tends to infinity of the sequence xk plus 1 so on till infinity, which again I have defined as infimum of k, and which is basically infimum of superior of k into xn. Let this be x star. So we have discussed about lim inf and lim superior in the last lecture. So similarly we have lim n tends to infinity, lim inf xn is equals to limit k tends to infinity, infimum of the sequence xk plus 1 so on, which is equals to infimum. Basically this is an increasing sequence, so it will have a supremum of k with infimum of n greater than or equals to k, which is equals to xn, which is equals to x star. So in the last class I have taught that limit n tends to infinity xn may not exist but because this is a monotonically decreasing sequence that is bounded below, hence this converges, and this is monotonically increasing sequence that is bounded above, it increases. So limit exists. So both the limits, these do exist. Okay. So, okay. Let us come back to. So this is something that we did in last class. I'm just recapping things. Okay. So now alpha k is defined to be supremum of xk plus 1 and beta k is equals to infimum of xk plus 1 so on this thing. So basically lim n tends to infinity supremum of xn is equals to limit k tends to infinity alpha k and lim inf of n tends to infinity xn equals limit beta k tends to infinity. So this is basically equals infimum of k, supremum of k greater than or equals to n times x n. This is basically supremum of k, infimum of k greater than or equals to 10 x n. So these are something that we have discussed in the last class. So by the definitions, you know that x star, which is equals to limit n tends to infinity, infimum of x n is less than or equals to limit n tends to infinity, supremum of x n. So for every sequence, we can basically construct things this way. So now we have a sequence xn, and alpha n is basically supremum of xn plus 1, so on, and beta n is equals to infimum of xn plus 1, so on. Implies beta n is less than or equals to xn, which is less than or equals to alpha n for all n natural numbers n. So because this is a monotonically decreasing sequence and it has a limit that is basically x star. So similarly, this also has an upper bound which is x star, implies beta n is less than or equals to x star, which is less than or equals to xn, is less than or equals to x star, which is less than or equals to alpha n. So this is something that we have for now. So why do we basically need all these things? So say tomorrow morning you solve a machine learning algorithm and you get a particular sequence of functions solving your optimality problem. Say this is f1. So you're basically solving your problem and you get a sequence of functions as the solutions. This is xn, this is xn. Okay, you can't say much about its convergence, but at least you can say that okay, this must have some limit superior and this must have some limit inferior, and so on about the solutions. So now I come to my main theorem. If x star, which is equals to lim n tends to infinity, supremum of xn equals limit infimum of xn n tends to infinity is equals to x star, implies that sequence converges to some value which is equals to x star, limit infimum and limit infimum, and if this holds, conversely holds. So this implies if limit inferior and limit superior are the same, it means that the sequence is convergent, and if the sequence is convergent, it means that limit inferior and limit superior are the same. Now we prove this. First, I assume that the sequence is convergent, implies I have to prove that x star is equals to x star. So now we have xn converges to x, implies there exists an epsilon greater than 0 such that for every n naught, for every n naught greater than or equals to n, implies x minus epsilon should be less than xn less than x plus epsilon. This is basically we get from our convergence definition. But by the definition of lim-inf and lim-sulf, alpha n is equals to supremum of xn, xn plus 1 plus 1, implies xn should be less than or equals to alpha n. Similarly, beta n equals infimum of xn, xn plus 1, so on, implies beta n is less than or equals to xn. So just see, from convergence we know that x minus epsilon to x x plus epsilon, ये interval में all your xn plus 1 so on till infinity must be in this particular ball. So it means that alpha n and beta n should belong to this particular thing, and by the definition of things, x minus epsilon should be less than or equals to beta n, which is less than or equals to xn, which is less than or equals to alpha n, which is less than or equals to x plus epsilon. So now what do we understand from that? Implies beta n and alpha n are converging and they converge to x. So which is basically x star comma x infimum. This is by definition. That's how we proved it. Okay. So now I'm going to just state two theorems. I won't do the proof is left to you. They are pretty straightforward from the definitions that we got. Okay. So if xn is converging to x, there exists a subsequence xnj maps from some natural numbers to R obviously, such that it is convergent. Pretty obvious, right? Okay. Now we have another theorem. If xn is bounded sequence, then it has a convergent subsequence xnj such that it converges to x star, which is equals to lim n tends to supreme of xn. Okay, so by the definition of xn, alpha 1 is equals to supremum of x1 so on x2 so on to xn. So the maximum value of this particular bounded sequence is attained at some particular xn. So let that be x tilde 1. So okay, so you have this supremum, right? See, if compare these two numbers, so choose whichever is the highest among them. Say it's x1, so you say it x1, then you go to x3. If x1, you compare x1 and x3, choose which is higher. If x3 is higher, you choose this one, then you go to the next number and so on. So on, you pick out the largest number possible. So it is basically attained at some kind of, say, x and j, some jth element, we call that as x and j. So now again at alpha 2 is equals to, you repeat the same process for x2 so on till infinity, you get some other number xn. But note that because you're just plucking out first element and choosing a supremum from this other set of elements, you will get x and j, some xn of j plus 1, which will be greater than or equals to x and j. So similarly, you get a subsequence that eventually converges to the lim sup. Okay, see, for now things look very abstract and stuff, but eventually when you solve an optimal, when as control engineers or machine learning engineers, later we go on solving some objective function, we try to minimize some objective functions and we get a series of solutions. At that point you have to do this boring, rough, abstract math to prove your hypothesis. But then this seems interesting to me, so I hope it is interesting to someone who actually is. I think it's a God-given thing, that's kind of. Okay, now we go to the next sequence, next concept, Cauchy sequences. So a sequence xn is said to be Cauchy. Cauchy is a great mathematician, by the way. I hope xn is said to be Cauchy if there for every epsilon greater than 0 there exists an n comma m greater than or equals to n naught, then mod of xn minus xm has to be less than epsilon for all n comma m greater than or equals to epsilon. So for n comma m greater than n naught. See, you can't say to, okay, why do we need this concept? Say xn converges to some value x. Okay, you are having hunch that xn is a series that basically converges to a limit. But what if you don't know the limit? So far, okay, we have been using some tests. I mean, we have been proving that the sequence is convergent after computing the limit by some hit or trial or some engineering / mathematical intuition. Say if there are some problems in world, that our intuition kind of breaks us. So you need, at least you see that, so what you do is that instead of trying, okay, so instead of trying to prove that limit actually exists or not, you just look at the tail end of the sequence and see that if the tail of the sequence basically converges, becomes small and small, okay, then you conclude that a system is a series is Cauchy. Okay, so far we are in happy space called real numbers, R. R comma Rn, and these are happy spaces. Happy. You have nice things and everything. You can see convergences and everything. But there are some difficult spaces such as a vectors, such as set of continuous functions. You won't find that all functions which are Cauchy are actually, they are convergent. You won't do that. Similarly, some Sobolev spaces, it's 2, 0 comma pi, and so on and so on. Of course, I'm kind of telling some abstract concepts in a hand weaving way, but I just want to give you that there are some spaces that are far complicated than the real numbers and so on that we are dealing with right now. That their things are not that easy. They are infinite dimensional in nature, and all convergences, you can't see the convergences. But slowly I'll just take you to, we'll go to those kind of abstract concepts. So now the first theorem. In reals, real number or Rn, happy space again, every convergent sequence is Cauchy. So how do you know that? So if Xn is convergent, implies Xn converges to X, implies mod of Xn minus X is less than epsilon for n greater than or equals to n0. Some n0 exists. Now just take this thing, mod of Xn minus Xn. So this is less than Xn minus X plus mod of Xn minus X. So basically adding and subtracting X and using the triangle inequality, which is less than 2 epsilon. So you can choose epsilon as small as possible. So these both go for all n comma m greater than or equals to n0. So every convergent series is Cauchy in reals. Okay, now I'll prove that every Cauchy sequence is bounded. Previously we have proved that every convergent sequence is bounded. So Xn is Cauchy implies there exists an n0 such that mod of Xn minus Xm is less than epsilon for all n comma m greater than n0, implies, just fix an n0, mod of Xn minus x0 less than epsilon implies mod of Xn less than or equals to mod of x0 plus 1 plus epsilon for all n greater than or equals to n0. So Xn plus 1, Xn plus 2, so on till infinity. Each of these number is basically less than or equals to mod of x1 plus epsilon. And this is one bound. And next bound is basically a maximum of x1, x2, so on till xn0 minus 1. So maximum of these two entities form the bound for our Cauchy sequence. So our Cauchy sequence is bounded. Okay, now I prove that every Cauchy sequence is convergent. Okay, so right now all of you must be confused. Okay, Pawan, you have taught about convergent sequences, and then you introduce the concept of Cauchy sequence. Now you are saying that all convergent series are Cauchy and all Cauchy sequences are convergent. Then why the hell have you brought this concept of Cauchy sequence? Because it's anyway convergent, right? But again, all this is happening in happy space called real numbers and some vectors of Rn. So in these happy spaces, happy spaces is not a technical word, I just used it like that. So in this space, so every Cauchy convergent implies Cauchy convergent, and convergent implies Cauchy. Cauchy implies convergent and convergent implies Cauchy. See, okay, so later on when we go to some complicated spaces such as set of continuous functions, such of Lebesgue square integrable functions, Sobolev spaces, and this thing. Of course, these are complete spaces under certain norms, but in infinite dimensional spaces, convergent will always imply Cauchy, but Cauchy need not imply convergent in infinite dimensional spaces. So when I start linear algebra, I'll discuss more upon what these infinite dimensional spaces are. But for now, we are in happy finite dimensional spaces of real numbers. So we have this particular property that every Cauchy sequence is convergent and everything. Okay. So now, if mod of xn minus xm is less than epsilon, so you have a Cauchy sequence m comma n greater than or equals to n naught. So now we take m is equals to n naught, implies mod of xn minus xn naught is less than epsilon, implies it is a bounded sequence. So implies xn naught minus epsilon should be less than xn by less than xn naught plus epsilon. Now by the previous method, let alpha n be the supremum of the sequence and beta n be the infimum of the sequence. So you get beta n less than xn less than alpha n less than xn naught plus epsilon. So you can choose epsilon arbitrarily as small as possible, right? Okay. So now what does this mean? This means that alpha n minus beta n should be less than or equals to 2 epsilon. You can choose epsilon as small as possible, implies the infimum of the sequences and supremum of the sequences are convergent, hence the sequence is convergent. So every Cauchy sequence is convergent. This is okay. So there are many magical things that are happening right now that people might not understand. So this is the beauty of real numbers. So say you only have natural numbers or only integers or only rationals. You won't have Cauchy sequence being convergent. So I think you see, why did real numbers come into the first place? So I have been talking about sequences, series, using some magical properties of magical mathematical properties. Properties of reals. So what are these reals? So what are these magical properties of real numbers? That unfortunately I have jumped. So we need to understand advanced mathematical concepts such as topologies, so on, so on. So because that will become more abstract, I don't have skipped all the time. I have started directly with the sequences and series which we can visualize. But there has been many abstract concepts working behind construction of real numbers such that we get these kind of properties. Okay, with that we have ended the discussion on sequences. Now I'll start with series. So we are done with sequences and now I'm starting series. So let Xn be a sequence. Then sigma adding all the elements I is 1 to infinity xi is called a series. Right. So you can write a series also as a sequence. Sn is equals to sigma I is equals to 1 to n xi. So basically if Sn converges to some s implies sigma I is equals to 1 to infinity xi converges to s. So basically series also can be written as some sequences, and now we'll see some examples. So the first example we have is sigma n is equals to 1 to infinity 1 by n into n plus 1. So this is something, an example from our IIT JEE / MTech MSET days, MSET / whatever your examination is. So this is 1 by 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus so on till infinity. So what do you think the value of this be? Any guesses on what the value of this summation is? Okay. So 1 by n into n plus 1 can be written as 1 by n minus 1 by n plus 1. So this can be split as 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 3 minus 1 by 4 plus so on till infinity. So which is equals to 1. Right. This will get cancelled and so on. But this is a childish way to prove things. Sometimes these childish things won't work. So we need some theorems and everything to actually establish our claims. So now we have a theorem. Sigma n is equals to 1 to infinity xn converges if and only if mod of Sn minus Sn is less than epsilon. So because we define the sequence Xn this way, sigma I is equals to 1 to n xn. So this is convergent only if and only if Sn is Cauchy, which implies mod of Sn minus Sn has to be less than epsilon for n comma m greater than 0. So this implies this implies this, and this implies this. It basically comes from the previous theorem, only just that you need to look it in a different notation, that's it. So if sigma n is equals to 1 to infinity xn converges implies limit n tends to infinity xn should be 0. Okay, I won't be proving this theorem robustly. It's kind of easy. It's the derivative of the previous theorem. So, but you see, right? So basically, you have a series 1 plus 1 by 2 plus 1 by 4 plus so on till infinity. You know this value, right? It's 2. And it's happened because all the tail end 1 by 2 power n is basically going to 0. So basically if the nth element does not tend to 0, we will be having some finite value here. So some finite value into infinity is infinity. Hence you won't see that the summation to converge. Basic stuff. Okay. Now we have a theorem. An absolutely convergent sequence is convergent. So what's an absolutely, so basically you have a series 1 to infinity xn. This absolutely converges if n is equals to 1 to infinity mod xn converges. So positive values of each sequence must converge. Okay, that's kind of easy to see. So now I'll just give some tests that all of you are familiar with. Comparison test. We all studied in our BTech first year days. Comparison test and root test. So basically if 0 is less than or equals to xn is less than or equals to yn. So if sigma n is equals to 1 to infinity yn converges, implies sigma n is equals to 1 to infinity xn converges. If sigma n is equals to 1 to infinity xn diverges, implies sigma n is equals to 1 to infinity yn diverges. And say if you have a sequence xn, if limit n tends to infinity xn power 1 by n is 1 by n is equals to L. If L is greater than 0, implies the summation converges. If L is greater than, this is 1, implies the summation xn diverges. So these are two tests. I'm omitting the proof of them. They're kind of very trivial. Basically, something that we have studied in our BTech. This is just a recap of that. So I'll be giving more examples and everything. If you want exercise on this, please do message me and everything. We can talk about that in detail. So for today, I'll end the real analysis part of our course and just begin with the PDEs. So last time we have talked about theory of distribution and the reasons why we need to generalize the notion of a function. So now, I'll just ponder upon this idea for a long time. So now, the PDE part. So all those who are not that interested in the partial differential equations thing can skip these things. It's fine. I won't feel bad or anything. Okay. So d of omega is basically all functions phi from some omega being an open set in Rn to R such that phi belongs to C infinity of omega, and support of phi, support of phi is subset of Rn, and support of phi is compact. So these are basically a space of infinitely differentiable functions. So just a recall that support of a function phi is equals to all x belongs to omega such that phi does not vanish there, and this has to be the closure of that. So now we have a vector space. We would naturally want to establish a topology. On d omega. So topology, okay, so people who are actually non-mathematical background or engineering background, it's a fancy word. So basically we are introducing a notion of distance, on a set. Distance in the sense some continuity or distance on a set. That's it. I mean, this will give you some intuition on that. Okay, so the topology that we are going to introduce on the d omega set is if a sequence of functions phi n belongs to d of omega. So we say that they converge to 0 if all the derivatives of phi n dash, phi n double dash, so on till infinity, all the derivatives, they converge to 0. Then it's a basically basic notion of topology. So if phi n belongs to d of omega is said to converge. So again, sequence and series converge. So sequence and series are like the basic breakfast of any mathematician. They are said to converge 0 in d omega if in support of phi n being a compact set, phi n and so on, phi n dash, all the derivatives must converge to 0 on this compact set. Okay. So now a definition. So far we have been trying to understand what a distribution is. So basically a continuous linear functional T maps an element from d of omega to R is a distribution if phi n converges to 0 by the topology that we have given before, d of omega. D of omega implies t of fn should also converge to 0. So basically from this you can see that the space of distribution is basically dual space of d omega star. Okay, now another definition. This is all for PDE guys. All those who are working in PDE should actually learn this stuff, without which you can't perform finite element analysis, prove some convergences in finite element analysis and so on. So omega Rn is an open set, and a real valued function, obvious, okay, real valued function, a real valued function f is said to be locally integrable on omega if for every compact subset of omega, integral of mod f d mu on the compact set should be less than plus infinity. So basically this is denoted by this particular notation. It's called L1 low. So all such f belongings to L1, obviously, such that if it belongs to L1, it also belongs to all such functions such that mod k, mod f on some measure d mu should be plus infinity for all k compact in omega. So this is a function of locally integrable functions. Just that the integral should be finite. We are just giving some more fancy terms on that. Okay, so now I'll give you an example of a locally compact integrable set. So now take function R2 mapping to R, defined by this particular map x1 and x2. So this is basically this is okay, this is a happy continuous function, so it is integrable everywhere. Only thing we have to look at is its integrability at 0. For that, we take a small ball in R2 and try to integrate this function in the small ball. So integral b 0 comma r under root 1 by under root 1 x1 square plus x2 square dx1 dx2, which is equals to, basically I am just doing some polar coordinate change, 0 to 2 pi 0 to r under root of 1 by root r into r dr d theta. So basically this is r into 2 pi, right? 2 pi r. So the integral of this particular function is basically 2 pi r, and as r goes to 0, the integral also goes to 0. So this is basically a locally integrable function. An integral function anyway. Okay, now we go to some so I'll be doing heavy duty examples now. Heavy duty examples on what a distribution is. So just recalling it, what definition of distribution. So basically a distribution is a bounded linear map from infinitely differentiable functions to real numbers. So example 1. So I define some PF. So basically your distribution should take a continuously differentiable function and give out an integral. So I am going to take omega f phi d. So how do we show that this is a good boundary linear map? So TF of phi so should be it basically only works on the support of phi, hence mod of integral support of phi into f phi d mu implies this is less than or equals to mod infinity. This is Cauchy-Schwarz inequality, and then into integral of support of f into mod f dv. So because this is a locally integrable function, this is a finite value, and this is a compact set. So it's a well linear map. Also, it's continuous. So now we have a theorem. I'm just going to state this theorem. I'm not going to prove it. It requires far more mathematical details than what we have. So if f is a locally integrable function of omega, and for every phi belongs to the infinitely differentiable functions, then and integral of f phi dx is 0 for all phi. This will imply that f is 0 everywhere except on a set of non-zero measure, except on a set of zero measure. It's just okay. Now I'll just prove that a distribution is a bijection. So if f comma g belongs to L log 1 of omega, and if Tf is equals to Tg, to prove that it's a bijection, to prove that it's an injection, f should be equals to g. So implies if Tf is equals to Tg implies integral of f into phi should be equals to integral g into phi. This implies integral f minus g phi should be 0. By the previous theorem that I have stated, if f phi is 0 for all phi, implies f is 0. So implies from here f minus g is 0. Implies f is equals to g on a set almost everywhere. So if Tf is equals to Tg implies f is equals to g. So distributions are it's a bijective kind of a thing. So with that, I guess I'll end the class for today. Okay guys, stop the recording.